Let's take a look at the recursive linear growth model. P sub 0 equals A, so that's the initial term. P sub n equals P sub n minus 1 plus D. Now this formula form is a little bit confusing to learn first, but once you see what it is, it's really not that bad. So first off, our first example, P sub 0 is given in the first part of the definition. So that makes the first term, P sub 0, very easy to get. Next up, the plus D is the constant term. Now, you might actually have it look like this, in which case the constant term is in front. So don't get used to that it's on the right. Get used to it's the constant term, the one without the p variable anywhere. So the D value is also very easy to spot in this recursive definition. However, this is where it gets a little bit more difficult for students to figure out the next few terms. One thing is you can jump straight to the other explicit model because we have P sub 0 and D. So for example, this first problem, since we have D is 3 and P sub 0 is 1, we could actually write this as 1 plus 3n. And now plugging in 1 into that, plugging in 2 into that, would be really easy to find. 1, that would be 4, and plugging in 2 times 3 is 6, plus 1 is 7. However, we don't want to rely on that necessarily, because when we get to other types of recursive models, there won't be as nice of, or even any, explicit model to convert to. So let's practice the other way. In order to find P sub 1, if we go to this formula and plug in 1 for n, that would tell us P sub 1 equals, here we have 1 minus 1 is 0, P sub 0 plus D. And we know P sub 0 for this problem, it's 1. And we know D for this problem, it's 3. And in that way, we could generate the value of 4. Now, if I wanted to find P sub 2 in the recursive definition approach, we would plug in 2 for n, giving us this formula, P sub 2 equals P sub, now here we have 2 minus 1, that's P sub 1 plus D. We know what P sub 1 is because we just found it. P sub 1 is 4. And D is still 3. It's a constant. There's 7. So in this way, we can use the actual recursive definition to generate terms one at a time. Okay. Now for the next example. We know we started off at 32. And this tells us that the D value is negative 4, so we're going to subtract 4 to get to the next term. So if we just subtract 4 from 32, we will get 28. And then subtract another 4, we get 24. So we can also interpret the linear growth model, the D value, as literally the first example is an add 3 sequence starting at 1, plus 3 is 4, plus 3 is 7. The next one is a subtract 4 sequence starting at 32, subtract 4, 28, subtract 4, 24. So we can convert to an explicit model that we can just plug values in to find terms. We can do them one at a time using the formula that's provided, or we can understand that this is linear growth, and therefore it's either an add or a subtract sequence. The last way that I want to demonstrate requires you to have a calculator that has an answer button on it. Now, I'm using a graphing calculator, but the TI-32, the 30XS, the 36 Pro, there's a lot of versions of the scientific TI calculators that do have this little answer button. This makes it very efficient to do recursive modeling. So let me demonstrate. You would start off by putting the first term, 1, for the first problem. We already have the first few, so I just do it again, 1, and hit enter. Now, for the recursive definition, wherever you see the p sub n minus 1, you replace that with answer. So we would have answer plus 3. So that would be answer plus 3. What the calculator is going to do is it's going to use 1 for the answer spot, and then it's going to add 3 to that, and it should give us 1 plus 3 is 4. There's their next term. Now the nice thing about coding this with the answer button is now the answer is 4. And if I hit enter again, it will redo the answer plus 3 formula, but now the answer has 4 in it, and it'll be 4 plus 3, 7. Hit it again, next term. Hit enter again, next term. And again, and again, and again. And in this way, you can use your answer button to generate the recursive defined sequence of numbers. So for the second one, that would be 32. Start it off, and then answer minus 4. Answer minus 4. Not negative sign, that would give you an error. It has to be a subtraction in this problem, minus. And then 32, then 28, then 24. This would be p sub 3, p sub 4, p sub 5, etc. So for our last one, just to demonstrate, if we started at negative 4, now we need the negative sign, negative 4. That's our first term. And then answer minus 1 will be the term generator. Hit enter, negative 5, negative 6. There we have our next terms of the sequence. So this gives you a third, well, I guess it's a fourth approach to fill these out. The first approach, find D and p sub 0 just by knowing where to look. There's p sub 0, there's D. And then create the explicit model, or go through the formula approach, or understand what the linear definition is, add 3 or subtract 4 or subtract 1, or now a new calculator approach. The calculator approach is going to generalize nicely to the exponential and logistic models, so I highly recommend, if you have an answer button, to practice those. And now go ahead and pause the video and do the last 3 examples with whichever method, or maybe one method per problem, and see what you get. So the answers. D is 2, first term 6, and then 8, then 10. Answer. D is 50, and then, first term is, D is negative 5, I'll get there. First term is 50, then 45, then 40. Okay, D is negative 0.1. The first term is 2.5, then 2.4, then 2.3, etc. All right, this is your recursive linear model examples. I hope this makes sense.